So here we are in chapter 9. We're looking at chemical bonding. Big things we're going to move to is Lewis structures. That's kind of the big hallmark for this chapter. I will say this is definitely a chapter to be careful of, because if you don't get how to do Lewis structures by the end of this chapter, the next chapter is going to make no sense whatsoever. So just throwing that out there. So before we talk bonds, we need to talk types of bonds. So again, anytime we have atoms or ions strongly attracted, there is a chemical bond taking place. There's three main types. Ionic bond, which is positive and negative ions attracted to each other, kind of like the north and south ends of magnets. And what we're usually going to see is between metals and nonmetals. We have the covalent bond, which is a sharing of pairs of electrons, and that's generally going to be between two nonmetals. And finally, we have the metallic bond, which is between two or more metals themselves. And in this case, the bonded electrons are actually free to move around, and that freely moving electrons is what allows metals to conduct electricity so well. So, very short section. So kind of bundling in together 9.3 and 9.4, Lewis symbols, lattice energy, and ionic bonds. So what these kind of Lewis symbols are is a way of showing the valence electrons in an atom. And again, we use these to track what the electrons are doing during bond formation. So the Lewis symbol of an element will consist of the chemical symbol for that element with a dot around it, one for each valence electron. So like this would be the Lewis structure for sulfur. Notice in this case, because sulfur only has 6 valence electrons, which is what we should expect, that it's 2 pairs of 2. And that's because we kind of use the 4 sides of the atom in general. And what we generally do is we kind of put one dot on each side before doubling them up. Now, which sides are doubled up doesn't matter. Again, the dots are placed on the 4 sides, top, bottom, left, and right. Each side can have 2 electrons, blah, blah, blah. All 4 sides are equivalent, doesn't matter. And we can easily tell how many electrons, valence electrons something have is, if it's a representative element, whatever its group number is how many valence electrons it has. So this then leads us to the octet rule. Octet rule states pretty simply that atoms are going to gain or lose electrons to be like a noble gas. And that's because the noble gas electron configurations are stable. All noble gases, with the exception of helium, which only has 2, have 8 valence electrons. So the octet rule says atoms tend to gain, lose, or share electrons until they're surrounded by 8 valence electrons. In other words, we're filling up their highest energy level S and P sublevels. And this actually does fit with helium. Helium's in the first energy level. There's only a 1s, and it's 1s2, so its S sublevel is filled. There is just no P sublevel in the first energy level. And again, that means that we'd be seeing 4 pairs of electrons around that Lewis structure. So, ionic bonding. When metals and nonmetals react, what we envision is this electron transfer from the metal to the nonmetal. Now, there's going to be 2 properties that we saw back last chapters that indicate how easily this occurs. First will be ionization energy. Again, that's kind of a gauge of how easily electrons are removed from an atom, and electron affinity, how easily an atom takes electrons. And these 2 together kind of give us an idea of what's going on in this electron transfer. So electron transfer to form ions is going to occur when one atom has low ionization energy, which means it easily gives up electrons, which by the way is metals, and the other has a high electron affinity, which means it very readily takes electrons, which would be nonmetals. So properties of ionic compounds. They are brittle, they have high melting points, and they're usually crystalline. We'll talk more about this kind of high melting point and why that is when we get into chapter 11. So an example of sodium chloride formation. So there's sodium, there's chlorine. The electron is going to move from the sodium to the chlorine. Hey, look, they both now obey the octet rule. And now because one is positive and one is negative, they're going to have that electrostatic attraction, one being positive, one being negative. They attract, and we call that attraction an ionic bond. And one way when we do Lewis structures or Lewis symbols for ions, we generally put a hard bracket around it with the charge just to really drive home that point of the whole thing carries that charge. Not required, but don't panic should you see it. Now, the energetics of this are interesting. So this turns out this electron transfer process tends to be very, very exothermic. And we actually saw this a little bit because we did the redox chapter. And redox reactions tend to be very, very exothermic, and that's a transfer of electrons. And what we see is that Appendix 2 shows heats of formation of ionic compounds. They tend to be very negative, again, very exothermic. So how is this working? So removing an electron from an atom is always endothermic. That ionization energy is always energy put in that is endothermic. So again, going from sodium to sodium plus requires 496 kilojoules per mole. That's a pretty substantial amount of energy to remove one electron from a mole of sodium. But adding an electron to a nonmetal tends to be exothermic. So for instance, adding an electron to chlorine releases 349 kilojoules per mole. That's its electron affinity. Now if you notice here, we have an input, an endothermic of 496, an output, an exothermic of 349. If this was all that was in play, this really wouldn't be exothermic. This would actually be endothermic. Looks to be, what, 250 something, so around there, 150 something. I'm doing mental math, is not what I'm doing right now. Anyway, so if this transfer of electrons, this removal and depositing of the electron was the only thing happening, again, this really wouldn't be an exothermic process. In fact, this reaction wouldn't be exothermic, so there's something else going on. So, what's the other thing? It turns out that ionic compounds are stable primarily because of that attraction between ions with an unlike charge. And it's this attraction that draws the ions together. This attraction releases energy and causes ions to form a solid array or a lattice. So, a measure of how much of the stabilization, how much energy comes from arranging these oppositely charged ions into a solid is given by its lattice energy. Technically, we find lattice energy by figuring out how much energy is required to completely separate a mole of an ionic compound, but we can revert, and that would be wildly endothermic to separate all the ions in an ionic compound, but we can kind of run that backwards, and that flips the sign of the heat. So that's kind of what lattice, so yeah, that we find lattice energy through breaking apart ions, but we use the lattice energy, that exothermic release of kind of run it backwards, and that's how much energy is released when the ions come together. So for instance, the lattice energy here is 788 kilojoules per mole. Hugely, in this case, again, this is to break them apart. Again, we're breaking it apart. Again, extremely endothermic, but we're concerned about the reverse process, the joining of them. Because we're just reversing the reaction, we then reverse the sign, making it extremely exothermic. So that means that all in all, we have that endothermic process of removing the electron, the usually exothermic process of the nonmetal taking it, but then the hugely exothermic process of that lattice energy. Now, this is important. For a given arrangement of ions, the lattice energy increases. You release more energy as the charges on the ions increase and their radii decrease. This is Coulomb's law. More charge means more attraction. More attraction means larger lattice energy. Smaller radii means they can get closer to one another. Closer charges means greater attraction, and again, greater attraction means greater lattice energy. So lattice energy is going to depend both on the charge and the closeness of the ions, so the size and the charge. So an example, which of the following would we expect to have the greatest lattice energy? So we have AgCl, CuO, CrN. And what I would recommend doing, don't worry about ion size unless you're comparing things of similar charge. But in this case, the CrN, chromium's a 3+, nitride's a 3-. Huge charge differential there. That copper would be a Cu2+, oxide's always a 2-, and the silver chloride. Silver's always a +1, chloride's always a 1-. So just simply based off the charges, we should expect that chromium-3 nitride to have the greatest lattice energy, and it does by a pretty wide amount. So electron configurations and bonding. So even though the lattice energy itself increases with increasing ionic charge, you're never going to find an alkaline metal with a 2+ charge. So we have to think about this. So why, even though the lattice energy would be greater Why wouldn't sodium have a 2 plus charge? Why aren't ions maximizing their charge? So again, Na2 plus is wrong, Na plus is right. Why is this? Well, because to make an Na2 plus, even though it would have a significantly greater lattice energy, the ionization energy is just so much larger that it doesn't make up for having to remove that inner shell electron. Likewise, you'll never find a Cl2 minus ion, even though having sodium chloride with the chloride having a 2 negative ion, charge, that would give a greater lattice energy, but once chlorine's gained 1 electron to form bichloride, the electron affinity is just terrible. You have to put so much energy into it to make that happen. It's just not going to. So, some periodic trends. Generally, if we're talking metals from 1A, 2A, and 3A, again, they're going to be cations of charges 1, 2, and 3 respectively. We know this. We learned this in normal chemistry. For ionic compounds from groups 5, 6, and 7A, we're going to be seeing anions of 3 negative, 2 negative, 1 negative. So again, that's the nitrogen group, oxygen group, and the halogens. And we're generally not going to find ionic compounds of nonmetals in group 4A, so like copper, silicon, germanium, because really seeing charges more than 3 is pretty darn rare. Now, transition metal ions. So what we see is the lattice energies of ionic compounds usually is only large enough to make up for the loss really of 3 electrons. That's why we generally only see cations of +1, +2, or +3 charge, generally. Now, it turns out the octet rule is broken by most transition metals. Because when forming ions, transition metals lose the valence shell electrons first, then as many of the d sublevel electrons are as needed to reach the charge. So for example, with iron. So iron, this is iron's electron configuration. When iron forms an Fe2+, it's actually going to lose the 4s2 electrons first. It's losing the valence electrons first. But notice, this is not the electron configuration of argon. It has that 3d piece to it that argon doesn't. Now, also note when it's forming iron 3+, iron 2+, and iron 3+ being the common charges that iron will have, it not only loses that 4s, but then that last electron comes from that d sublevel. And that's how we deal with ions with transition metals. And again, this is creating what's called a pseudo noble gas configuration because it's argon with that extra d pieces thrown in there. Polyatomic ions. So several cations, and there's lots of anions, are polyatomics like ammonium, carbonate, and in these two, and all of them really, 2 or more atoms are bound together by really covalent bonds. But they form a stable group that carries a charge. The entire group gained or lost a certain number of electrons to give us the appropriate charge. And that's really the only thing you need to worry about with polyatomics. We'll work about the Lewis structures for those later this chapter. Okay, so we've looked at ionic bonding. Now we're going to look at covalent bonding. Again, the biggest category, so if we're not dealing with ionic bonds, we're dealing with covalent bonds. Covalent bonded things usually have low melting points. Again, we'll talk more about that relationship in chapter 11. They're pliable, you can bend them. And again, what's happening here, instead of this transfer of electrons, it is a sharing of a pair of electrons. So with hydrogen we see here, so here's 2 hydrogen atoms, here's their Lewis structures. What's happening is the 2 positive nuclei are repelling each other. The 2 negatively charged electrons are repelling each other, but the nuclei and electrons are attracting each other. It's like the nuclei of this hydrogen is attracted to that electron, this nuclei is attracted to that electron, and this kind of shared middle ground here, that's effectively what the bond is. Now, because this is a stable molecule, it does tell us that those attractive forces of the nuclei to that other electron is greater than the repulsive forces would be. If the repulsive forces were larger, we wouldn't see this molecule. So again, the nuclei are attracted to the negative charge, the electrons, and the shared electrons between them. And those shared pair of electrons acts kind of like the glue to bind those atoms together. But again, don't think of a covalent bond or even an ionic bond as a thing. It's just that attractive force, in this case, between nuclei to those shared electrons. So, Lewis structures. Right now, it's going to be all about the octet rule. So here's my 2 hydrogens. They go together. We see those electrons share between. So this hydrogen on the left sees it having both electrons. This hydrogen sees it having both electrons. Each hydrogen is seeing it has 2 electrons. That's meaning it is meeting the octet rule, because now each hydrogen sees that it is gaining that same electron configuration as helium. Hey, look, I did the same thing I did there. Chlorine, same difference. Ooh, look. Now, when writing Lewis structures, we usually only show electron pairs as a line and the unshared electrons as dots. This is not a requirement, just as a FYI. So the previous examples would look like this, just what they are. For nonmetals, the number of valence electrons will be the same as the group number. So group 7A, they all have 7 valence electrons. Because they have 7, they only need 1 more, so they're going to form 1 bond. Group 6A has 6 valence electrons, so they're going to form 2 bonds. That could be a single bond or a double, so 2 single bonds or a double bond. We'll talk more about those. Group 5A has 5 valence electrons, so it's going to need 3 more, so it's going to form 3 bonds. So it could be a triple bond, a double bond and a single bond, or 3 singles, some variance in there. Or group 4A has 4 valence electrons, so this would be like your carbon. So it's going to need to form 4 bonds. Again, some mixing, matching, like a single and a triple, 2 doubles, 4 singles, something like that. Now, multiple bonds. When 2 atoms share a pair of electrons, we call that a single covalent bond or just a single bond. With many molecules, atoms will follow the octet rule by sharing more than 1 pair of electrons. So again, if you're in group 4A, 5A, 6, or 6A, you're going to share more than 1 pair. So you're going to need more than single bonds, oftentimes. When there's 2 pairs of electrons are shared, we draw 2 lines. We call that a double. So we're going to look at an example of a double bond here. And we see carbon, we see oxygen, we see oxygen. Now, oftentimes we can kind of play this connect the dots sort of thing, find the lone thing. So here's kind of one bond that's going to form. Here's a second bond that'll form. Okay, I made that really more terrible than it had to be. Here's another, and here's another. So the end result would be that carbon in the center connected to 2 double bonds on either side. And then each oxygen would have 2 lone pairs. Another example, so we can talk triple bonds. It's when 3 pairs of electrons are shared. Great example of this is nitrogen. So here are 2 nitrogen atoms, and again, we can do that connect the dots thing. So this is going to be terrible. We go there, there. I've made this way harder than it has to be. Made that way, way harder. So it's 3 in the connection, so we would see a triple bond and a lone pair on each nitrogen. Now, properties of nitrogen actually follow that Lewis structure. They're very, very stable, and that's because of that triple nitrogen-nitrogen bond. Again, one of the first steps in a chemical reaction is breaking apart those bonds. Triple bonds are pretty strong. It's 3 bonds. So it's stronger than a single bond, stronger than a double bond. Nitrogen's diatomic. That's because 2 nitrogens together means that both nitrogens are meeting the octet rule. And it's a short bond. It turns out, and this is kind of what we talk about bond length, that the distance between the atoms depends on the number of bonds. More bonds means shorter bond length. So single bonds would be the longest, double bonds in the middle, triple bonds being the shortest. So let's talk bond polarity, so section 9.6. Now when 2 identical atoms bond, the electron pairs are shared equally. But if I contrast this with an ionic compound like sodium chloride, there is no sharing of electrons. So, and again, that's a transfer of electrons. For most covalent substances, these bonds occur somewhere between these 2 extremes of complete transfer or equal sharing, meaning there's unequal sharing. Now to talk this, we have to talk what's called electronegativity. Electronegativity gives us an estimate to let us know if a given bond is nonpolar covalent, polar covalent, or ionic. What electronegativity is, it's the ability of an atom in a compound. We only consider electronegativity when it's an atom in a compound to attract electrons to itself. In other words, it's how strongly it holds on to those electrons in a covalent bond, or just in a bond in general. The greater an atom's electronegativity, the greater its ability will be to attract electrons. Electronegativity is related to both its ionization energy and its electron affinity. So an atom with a very negative, that means very high electron affinity and a high ionization energy, will tend to attract electrons from other atoms and resist having its electrons attracted away, which means very high electronegativity. General trends, electronegativity increases from left to right, and electronegativity decreases as we move down. Easiest way to deal with electronegativity is that fluorine is, by leaps and bounds, the most electronegative element. What I like to do is just kind of figure out how close things are to fluorine. Elements that are similarly close to fluorine, either vertically or horizontally, should have similar electronegativities. So yeah. And here's kind of the chart on that. Again, it's not a perfect analysis, but it works most of the time. So bond polarity. So we use difference in electronegativity to figure out if a bond is polar. So what we can do is we just subtract the two electronegativity values from each other. That tells us what type of bond we're looking at. Here's some examples. So again, we have nonpolar. That means equal sharing of electrons. We get polar, which means unequal sharing, but still sharing. And at extreme levels, it's ionic. So again, in general, if the difference in electronegativities are less than a half, or 0.5 bond, it would be nonpolar. Again, that is equal sharing of those shared electrons. Between 0.5 and 2, we consider that to be a polar bond, and that means the more electronegative element is going to pull the electrons towards itself more. And what that does is it's going to leave a partial positive charge on the less electronegative element because the electrons are being pulled away from that end, making it slightly positive. Whereas the more electronegative element will have a slight negative charge because the electrons are being pulled towards it, and electrons again have a negative charge. And if it's greater than or equal to 2, then we're treating it as ionic, but again, that's metals and nonmetals. So for HF, so this is one way we can show it. So we have the lowercase delta sign there. We can put lowercase delta positive on the hydrogen, negative on the fluorine. Again, fluorine is leaps and bounds more electronegative than everything else, so that's going to be the negative end. Again, in summary, the greater the difference between the electronegativities between the two atoms, the more polar their bond will be. Nonpolar at one extreme, ionic at the other, most fall in between. So another example of bond polarity. So which of the following bonds is most polar? So we have SCl, SBr, and SECl. Oh, and SEBr. And to do this, we're going to use figure 8.6 on page 312 that has those electronegativity values. And all you do is you look up each element, subtract their electronegativities from each other, and whichever one has the biggest difference is the most polar. Now again, kind of eyeballing this, looking at a periodic table, so I see that sulfur is down and left 1 from fluorine, chlorine's right below it. So sulfur is a little bit further away. Sulfur and bromine. Bromine is 2 down, so I like to think for each kind of right or left would be a 1 difference, each up and down would be 1 difference. So for me, just eyeballing this, I would go, okay, sulfur is 2 away because it's down 1 and left 1. And chlorine is 1 away, so bit of a difference there. Sulfur, bromine. Sulfur is, again, 2 away. Bromine is also 2 away because it's down 2. Selenium, chlorine, so it looks like selenium is down 2 and left 1, so that would be kind of a 3. Chlorine is 1 away. And selenium, bromine, selenium still 3 away, bromine still 2 away. So the most polar one would be the biggest difference, so I would guess the selenium chlorine bond should be the most polar, but again, I'd want to double check looking up the values. Now this brings us to this dipole moment. Again, the difference in electronegativities back with that fluorine hydrogen example led to a polar covalent bond. So again, there's a concentration of negative charge on the more electronegative atom, fluorine in that case. Molecules like this where, and this is the fancy way of saying where you have these partial charges, where one end is slightly positive, one end is slightly negative, we call that a polar molecule. We can show that either by labeling plus and minus on either end, or this symbology here, we put the little cross plus end on the positive side and the arrow pointing towards the negative. See, that's what we'd see. Same thing. Now, why do we worry about polarity? Polarity helps us to determine many, many properties we see on the big level. This is what Chapter 11 is going to be all about in its entirety. Because what happens is because polar molecules have a positive and a negative side, they actually align themselves. So the positive ends of one will attract to the negative end of another. So you kind of get these big chains of molecules. Kind of holding it there. And also polar molecules will be attracted to ions because polar molecules have a positive end and a negative end, and ions have a positive ion and a negative ion, so those positives and negatives attract. So dipole moment. So whenever two electrical charges of equal magnitude but opposite sign are separated by a distance, a dipole is created. This is really a fancy way of talking about, so in a polar molecule, we have one end that's slightly positive, one end that's slightly negative. That means dipole is created. There is a quantitative measurement. It's given by this mu. You don't need to know how to calculate it. Here's the equation. Never need to worry about it. Do not worry about that. Now, the dipole moment will increase as the magnitude of the charges increases. More charge means bigger dipole. Bigger distance between the charges, bigger dipole. So again, it's really kind of back to this Coulomb's law idea. For nonpolar molecules, the dipole moment would be 0 because there is no separation of charge. Bond length. So as electronegativity differences decrease, the bond length increases. And that's just saying, again, as electronegativity differences decrease, so as it becomes more polar, the bonds get shorter. So, bond types and nomenclature. So we've seen ways to name ionic and molecular compounds, but interesting to know, when we get to metals with high oxidation numbers like titanium here, the names blur a little bit. So like TiO2, that titanium has a +4 charge, we can either call it titanium 4 oxide or titanium dioxide, even though titanium is a metal. Because when we actually get to these high oxidation number metals, what we actually see happening is it's really covalent bond. They're really a molecular compound with that metal, non-metal business. We've just ignored that so far. Okay, we are looking at the most important section in this chapter. We're looking at section 9.7, looking at drawing Lewis structures. So, knowing Lewis structures will enable us to do there are two-dimensional diagrams of kind of what a molecule looks like. This is necessary to move to the three-dimensional structure, which we talk in chapter 10. And then we need to know those to be able to talk intermolecular forces, which is in chapter 11. So this is where things really start snowballing up. So again, we need to really break things down to the Lewis structure when we're talking properties of molecules. Now, because this is important, we're going to focus on how to draw them. It is a very step-by-step process. We're going to go through this. This is how I will always show you how to do Lewis structures, and we'll do some practice with them. So the procedure: 1, take all the atoms in the molecule and add up all their valence electrons so you get a total. Again, we don't care what electrons come from what atom, just add them all up. Add them all up. So like if I was doing NaCl, we'd add up to 8 electrons because sodium has 1, chlorine has 7. 7 plus 1 is 8. Next, we write the symbols for the atoms to show which atoms are connected to attached to which, and connect them with a single bond. So we kind of draw out the structure, very base structure, I call it the skeleton, and we connect everything with single bonds. And again, we're going to show a single bond with a single dash, and that means 2 electrons. Chemical formulas are often written in the order to which the atoms are connected. And you'll just kind of practice will help with that, especially once you start figuring out the rules for this, which we'll talk later in the chapter. So like HCN would tell me that it's hydrogen, then carbon, then nitrogen. So the carbon's bonded to the hydrogen, and then the nitrogen's connected to the carbon. When a central atom has a group of other atoms bonded to it, the central atom is written first. So like carbonate would have that carbon and the 3 oxygens attached to it. Now we're going to complete the octets around all the atoms bonded to the central atom. Now to do this, we're going to remember that hydrogen only gets a single pair of electrons, and then it's meeting the octet rule. Now, through all of this, I'm going to kind of take a step back from step 2 and 3. You're tallying up how many electrons you've placed. So again, from step 1, we know how many electrons we have to work with. As a note, if there's a charge, so like a carbonate ion has a 2 negative charge, we would add 2 more electrons to the total. For every bond I place doing the skeleton, we take 2 electrons away because every single bond is 2 electrons. For every electron I place to complete the octet around the outer atoms, 1 electron. Finally, we're going to place any, not finally, but then we place any leftover electrons on the central atom, and as we're going to see later this chapter, even if this violates the octet rule. And finally, if there's not enough electrons for that central atom to meet the octet rule, then what we'll do is we'll form multiple bonds. So the way we do this is we take one or more of the unshared pairs of electrons from an outer atom and turn that into like a double bond or a triple bond. We'll see this in examples. So again, we're working through examples. Let's do this. So PCl3. So looking at this, phosphorus is in group 1, 2, 3, 4, 5. So that's 5 valence electrons. Chlorine is 3 times 7. So we're looking at 26 electrons. So drawing the skeleton, so phosphorus would go in the center, P, Cl, Cl, Cl. So I've done that. Now by doing that, I've created 3 bonds. So that's used up 6 electrons, so I'm down to 20. I place around the outer atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I used up 18 electrons, placing electrons around the outer atoms. Finally, any leftover electrons, which we have 2, get placed on the central atom. We now are out of all of our electrons. Everything is meeting the octet rule. That it would be the Lewis structure for PCl3. Hey, look, that's what I just did. So drawing electron structures, let's look at another example. So HCN. So again, I add up all the electrons. 1 plus 4 plus 5 is 10. I add my bond, so we get this HCN. Now again, that used up 4 electrons total. So instead of 10, we now have 6. I'm going to complete the octets. Now note that hydrogen is already meeting the octet rule, because once hydrogen has any bond, it's done. So we're going to complete the octet. So 1, 2, 3, 4, 5, 6. Nitrogen's now meeting that. There's no leftovers to place. Look, that's what I just did. But now what we need is multiple bonds, because that carbon is not meeting the octet rule. So what we're going to do is take some of the lone pairs from the nitrogen and create a multiple bond from that. So carbon right now only has 2 bonds. It needs 4 bonds total. It needs 8 electrons. So we're going to take 2 lone pairs to create actually a triple bond there at the nitrogen. And these guys are gone. And that would be the Lewis structure for HCN. So last but not least, we're going to look at another polyatomic here. We're going to look at bromate. So looking at this, I'm going to first add up all the electrons. So bromine is 7. Each oxygen would be 6. So there's 3 of those, 3 times 6. And that single negative charge means I'm going to add 1 more. So we're looking at, let's see, 3 times 6 is 18, plus 7 is 25. So we're looking at 26 valence electrons. So I set up my base structure. So bromine in the center, Br, O, O, O. I just used up 6 electrons. That leaves me with 20. Again, I fill in the outer portion. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Leaves me with 2 left. Any leftovers get placed on the central atom. Now what we can do, and the way we should do this, but it's not required, put brackets around it. And I'm going to erase my work here so I can kind of have the proper, go away, there we go, the proper thing. And because it has a negative charge, I just put a negative there. That shows that whole structure has a negative charge. And that's so in section 9.8, which is what we're in. If I click this button, there we go. We're in section 9.8. We're looking at 2 kind of separate things involved with Lewis structures. So resonance is a thing that can happen where we have multiple equally good Lewis structures, and we'll talk about that. But then also what formal charges is a way to evaluate whether or not 2 Lewis structures are equally good. So again, they're kind of used together, but they're also different topics, and but I'll discuss both. Now, When we do a Lewis structure, in a lot of cases, there's multiple possibilities for different Lewis structures. So, and they'd all be obeying the octet rule. So we have to decide which one do we go with. And that's what formal charge is. So the formal charge is really a gauge of reasonableness of a structure. And officially what formal charge is the charge the atom would have if all the atoms in the molecule had the same electronegativity. But I like to view this as how it's important, which is all about how reasonable a structure is. So first off, how do we calculate formal charge? What we're going to do is we're going to assign electrons or just count. I think of this as it's a math thing. So what we do is we add up all of the unshared or non-binding electrons assigned to the atom in which they're found. You add them up. For any bond, you add 1 for each bond, or half the number of electrons in the bond. So if there's a single bond, you'd add 1. A double bond, we'd add 2. A triple bond, we'd add 3. So we add those 2 up. So we add up all the unshared electrons, then we add 1 for each bond. What we then do is we then subtract that number from the number of valence electrons in the atom. So it's number of valence electrons minus this number there. So let's just see how to calculate this, some practice. So we'll look at the cyanide ion. So that is, let's say this is a potential Lewis structure for cyanide. Now that carbon atom, so looking at that, I see there's 2 non-binding electrons. So that's 1, 2. And then there's 1, 2, 3, 1 for each bond. So 2 plus 3 is 5. So we're saying that 5, we're assigning 5 electrons to the carbon. Carbon has 4 valence electrons. So we do valence electrons minus the number we've assigned. 4 minus 5 equals -1. That's how it is. For the nitrogen there, so kind of I'll erase what I have. So for that nitrogen, I would see 1, 2 right there. Again, the triple bond would be another 3. 1, 2, 3. So that's 2, 3, 4, 5, 6. So, or 1, 2, 3, 4, 5. So 5. That's how I do math. Nitrogen normally has 5 valence electrons, so it would have a formal charge of 0. First check with formal charge is that the sum of all the formal charges should add up to the charge on the molecule. In this case, cyanide has this negative right there. So all the formal charges should add up to -1, and -1 plus 0 is -1. So that would be a reasonable structure. Again, that's what we see there. And again, the sum adds up to the overall charge, so it's reasonable. That is a reasonable structure. If I was doing something like water, because it has no charge on it, would be expected to have a formal charge of 0. Now again, what's the use of this? So we use formal charge to choose between alternative Lewis structures. We're trying to judge which one is most reasonable. So for instance, there's 2 possible Lewis structures for carbon dioxide. So we see carbon dioxide having these double bonds between each carbon and oxygen, or having a single bond on one side and a triple bond on the other. So we're going to go through each atom. So oxygen has 6 valence electrons. Looking at the numbers here, so I see 1, 2, 3, 4, 5, 6. So that oxygen would have a formal charge of 0. The carbon, no lone electron, so just 1, 2 from that double bond, 3, 4 there. By the way, carbon has 4 valence electrons, so we had 4 from each of the double bonds. So again, formal charge of 0. And then this oxygen on the right. So 1, 2, 3, 4, 5, 6. And we're always subtracting, gives us a formal charge of 0. That's looking pretty good. That's looking pretty good. Now again, carbon has 4 valence electrons. So now let's look at this oxygen on the left. I see 1, 2, 3, 4, 5, 6, 7 gives that oxygen a formal charge of -1. We'll look at this carbon here. So 1, 2, 3, 4. Again, every bond adds 1, so that's 4 minus 4, so that would be 0. And finally, on this one on the right, so 1, 2, 3, 4, 5. Now, both structures do follow the rule about the sum of the formal charges should add up to 0, or should add up to the charge on the molecule, which in this case would be 0. The kind of next step is that we want to minimize formal charge. Formal charges of 0 is better than formal charges of plus or minus 1. So that tells us in the end that this structure of carbon dioxide is more likely to be correct. It is more reasonable because it is minimizing the formal charge. Now again, in both cases, they both add up to 0. Again, it makes sense. So again, which is correct, just like I said. Guidelines for correctness. Generally, the Lewis structure in which the atoms bear formal charges closest to 0 is correct. That's what we want. But if we have to have formal charges that aren't 0, what we generally want is we want any negative formal charge to reside on the more electronegative atom. So given the choice of two structures, each having positive and negative formal charges present, whichever one has that negative formal charge on the more electronegative atom would be likely to be correct. So there's kind of 3 layers of correctness. First one, do all the formal charges add up to the charge on the molecule? If yes, move on. Now we're aiming for as close to 0 as possible, minimizing formal charge is better. And then the next part is if we have to have negative formal charges, are they on the more electronegative atom? That's how we do this. Now this then brings us to resonance structures. So sometimes we find molecules or ions where the arrangement of the atoms is not fully described by one Lewis structure. In other words, where there are 2 or more, you can tell this I'm doing it at school, 2 or more Lewis structures with the same formal charge situation. So for example, if I was to make ozone, so that's what we see kind of here on the left. And where I'm at that stage would be the, I've added up all my valence electrons, I've made my skeleton equation, or my skeletal structure. I've then added valence electrons around the outer atoms, then I've dumped all my remaining on the center. But that center oxygen is not meeting the octet rule. So we're going to take a pair of electrons. Here I do it from the top. Here I do it from the bottom. I can take a pair of electrons. I have a choice. I have not just a choice, I have an equivalent choice. In both cases, that pair of electrons is coming from an oxygen to that center oxygen. It's an equivalent choice, but it's which oxygen is providing that double bond. That's the difference. So there are 2 possibilities here. 2 possibilities. And when we have that, that's when resonance happens, and we can show that with this double-headed arrow. So again, with ozone, the placement of those atoms in the 2 alternative but equivalent. Because again, I had a kind of equal choice. Does the double bond come from the oxygen on the top or the oxygen on the bottom? So their formal charge would be really the exact same situation, but they're still 2 separate things. When that happens, when we have multiple possibilities where the only difference is which atom is providing a double bond, we call those resonance structures. So to describe ozone completely, we write both Lewis structures and we use that double-headed arrow between them to indicate that the real molecule is actually described by an average of the 2 resonance structures. Now, ye olde chemists used to think that the molecule would actually flip back and forth between the 2. But now we know it's a blend of the two. So the true arrangement is a blend or an averaging of the two or more Lewis structures. So with ozone, instead of there being a single bond and a double bond, and then it flips and there's a new single bond and a new double bond, that the two bonds, that single and the double, average out. And what we really have is something kind of like a 1.5 bond. That the true bond is somewhere between that single and double bond. Now, when we write resonance structures, you have to remember the arrangement of the atoms is exactly the same, only where electrons are placed. In other words, that double bond, where you have an equivalent choice of where a double bond is. That's the difference. So here's an example, a classic example of resonance, an organic compound known as benzene, C6H6. And again, there's this whole class of chemicals called aromatic molecules in organic chemistry. As you go further into chemistry career, you'll learn more about these. And one of the aromatic molecules is the hydrocarbon benzene, C6H6. And what we see is that the 6 carbons are bonded in a ring, 1 hydrogen each. And what we can see here is 2 separate structures. So we can see like here, there's a single bond, here there's a double bond, and it just goes around that circle. So there's 3 singles and 3 doubles, but where the singles are and where the doubles are change. So the true structure is kind of a blend between these. So all of those carbons have effectively what would be a 1.5 bond. And that's actually borne out through experiments. That bond is stronger than a single bond would be, but weaker than a double bond. And also remember that single bonds are longer, double bonds are shorter, triple bonds are the shortest yet. The lengths are somewhere in between as well. It really is like a 1.5 bond. So we're going to do an example with nitrate. So nitrate is NO3 minus. So basic Lewis structure, so I add up all the valence electrons. Nitrogen is 5. There's 3 oxygens. Each oxygen is 6, and that 1 extra because of that charge. So that's the 18, 19, so there's 24. So setting this up, I set up my skeleton. NO, O, O, that used up 6 electrons, leaving me with 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18. So I am now out of electrons. There's no electrons to dump on that central nitrogen, but that nitrogen is not meeting the octet rule yet. So I have to take a lone pair from an outer oxygen to create the double bond. But wait, there are 3 options here. So I could take a lone pair from this oxygen on the right and make a double bond. Or I could have taken a lone pair from the oxygen on the left and made a double bond there. Or, I know it's getting smaller and smaller with each one. It bugs me too. I could have taken a lone pair from this oxygen on the bottom. So this one actually has 3 resonance structures. So each of those oxygen-nitrogen bonds is around like a 1 1/3 bond, because that's, somewhere between the 3 different versions of it. So yeah, around a 1 1/3 bond. And this brings us to a bond order. This is a question that could appear on the AP test. It might ask, what's the bond order between these 2 atoms? It's simply the number of bonds between the 2 atoms. So if there's a double bond between 2 atoms, it has a bond order of 2. If there's a single bond, it's a bond order of 1. If there's resonance, then the bond order is in between. So for instance, with that nitrate, it would have a bond order of somewhere like 1.33. With the benzene that I saw, each carbon would have a bond order of 1.5. So yeah. Why am I repeating that? And here we are to turn everything you know about the octet rule upside down, that there are exceptions to the octet rule. So one thing that we find that the octet rule is not so much a rule as it is suggestions. And the octet rule sometimes will fail when dealing with ionic or metallic bonds, but it will also fail in many situations involving covalent bonding. There's 3 primary exceptions that exist. First, molecules and polyatomics, if they have an odd number of electrons. So if you add up all the valence electrons, you end up with an odd number. That can, you'll have to violate the octet rule then. It just happens. We often call these sort of molecules free radicals. This one is no longer tested on the AP exam, so we don't need to worry about it. And this is the most common where an atom has more than an octet. This one is very important and it will be critical moving into the next chapter. So let's start with the odd number of electrons. So in most molecules and polyatomics, the number of valence electrons will be an even number, and we can do this. But if there is an odd number, and it happens, then we can't get a full octet around each atom. And this will often lead to really odd resonance structures and situations where there's just a single electron by itself. So for example here, this would be resonance with the N and the O, and we can see this kind of lone electron is kind of all by itself. We call this free radicals. They're not good, and if you hear like antioxidants, foods like that combats free radicals. Compounds like this tend to be real reactive. They're not particularly stable, and having those in your body is a bad thing because they're so reactive. They'll react with what you don't want them to react with. But that's a pretty rare thing to see on an AP test. Now, this is much more common when there is more than an octet. So first off, we can only, this is going to be critical, and I've seen questions like this up here, and I've asked questions like this on TEPs, that this can only occur if an element is in the third period. Here I say higher, I mean like third period, fourth period, fifth period. So nothing in periods 1 or 2, so nothing in hydrogen's period or lithium's period. And the reason for this, excuse me, is to have more than a full octet, you need to have an empty d orbital, d sublevel, that's not being used to place those extra electrons. And d sublevels don't exist until the third energy level. 3d is the lowest energy sublevel that has a d. So yeah. But wait, there's more. Atomic size will also influence if an atom or molecule will likely take more than 8 valence electrons. What you normally want to see is a large central atom. And again, that kind of fits with the whole period thing, that once we get the third period, we're in third energy level, atoms are larger, but larger atoms do this better. So the larger the central atom, the more likely it is to be able to have more than an octet. Also, it's more likely if the central atom is surrounded by small electronegative atoms like fluorine, chlorine, and oxygen. I usually see this with fluorine, but I've seen chlorine as well, and oxygen sometimes. But fluorine and chlorine are the most common that we see here. Now, there are times when you can write an octet following Lewis structure and a non-octet following Lewis structure. Maybe because the non-octet following structure has better formal charge. In general, if you have the choice, octet rule trumps formal charge. I'm going to repeat that. If you have a octet rule following structure with bad formal charge, or non-octet rule following with better formal charge, err on the side of the octet rule. Most often this occurs when you just cannot fulfill the octet. And finally, this brings us into the last section, bond energy. I think this is the last section. This is a super easy section with one little twist, because there's always a twist. It's AP Chem. So the stability of a molecule is related to the strength of the covalent bonds that it has. The strength of the bonds is determined by the amount of energy needed to break the bonds. Stronger bonds take more energy to break. It's easier to relate bond strength to the enthalpy change where bonds are broken, because we go, okay, stronger bonds, harder to break. Pretty simple. So we can use what's called average bond enthalpies to estimate the enthalpy of a reaction. So we can find the bond enthalpies, which are just a table in your book, to estimate the overall heat of a reaction. Now again, in a reaction, what we're saying is bonds are broken, new bonds are formed, And this is really best for seeing if a reaction will be endothermic or exothermic. It is not as accurate as a true method of finding bond enthalpy like Hess's law or calorimetry or something like that. But it's a good way to tell if a reaction should be endothermic or exothermic. So it's pretty much a Hess's law type problem. What we use is we use the fact that breaking bonds is always endothermic. It always takes energy to break bonds, and we always get energy given off when new bonds are formed. So we view this in two steps. One, we supply energy to break the bonds in the reactants. Then we form bonds in the products that were not present. Here I kind of throw in this whole that were not present, in all honesty. And you could do it this way. You could only worry about the bonds that change, but really, and I'm going to be honest with you, take the extra time if you have the information and just do all the bonds of the reactants, all the bonds of the products, look up the values. You're less likely to make mistakes, because I think if you're trying to just focus on the bonds that are changing, you are more likely to miss one. So, the enthalpy of a reaction or heat of a reaction is estimated as the sum of the bond enthalpies of the bonds broken minus the sum of the bond enthalpies of the bonds formed. And again, that's just because bonds broken is endothermic, so it's positive. Enthalpies of bond form is exothermic, so negative. So broken minus formed, or again, sum of enthalpies of broken minus formed, or reactants minus products. And this is weird. I'm going to pause here for a moment. This is weird because every products and reactant situation we've seen with Gibbs free energy, we've seen with entropy, we've seen heats of reaction. It's always products minus reactants. Bond enthalpy is the reverse. Bond enthalpy is reactant minus product. It is opposite of the rest. You have to remember that. Bond enthalpy is reactant minus product. It is backwards. It is opposite of every other. So we know here's a reaction. Methane and chlorine produces methyl chloride and hydrogen chloride. So we can see this. And when I write things like this, what it really is so we have this hydrogen. We have 3. And then we have that 4th one there. What I'm really doing by writing it like this is emphasizing the things that change. Because we can see the CH3 remains the same in either case. It's that hydrogen carbon breaking, carbon chloride forming. We are breaking a chlorine-chlorine and forming a hydrogen chlorine. So that's what's shifting. So bonds broken, so we're breaking one bond of carbon-hydrogen, one bond of chlorine-chlorine. Bonds formed, we'll be forming 1 mole of carbon-chlorine, 1 mole of hydrogen-chlorine. And what we do is we look up, so this is just data given to you on an AP test. We would have to be given those bond enthalpies. And when you're doing mastering chemistry problems, use page 410 on table 9.3 for the values. And it's broken minus formed, or bonds in the reactants minus bonds in the products. So again, this is what we see. D would just be the number of moles. In this case, they're all 1. So I look up the values. So here's carbon-hydrogen, here's chlorine-chlorine, here's carbon-chlorine, and there's hydrogen-chlorine. And we get this. So this is telling us that that reaction is likely exothermic. But again, this actual value has a relatively decent amount of error to it, so it's not super useful if we want to know what the true heat of reaction is. It's, again, better for endothermic or exothermic. Again, generally, we only use these if we don't have the heat of formation values. So for instance, in your textbook in Appendix C, there is no heat of formation for that CH3Cl. So that's where bond enthalpies come into play. Now again, it's close. The actual delta H for this is 99.8, or negative 99.8. But again, you can see there's some error brought in. So it's not super accurate. It's not terrible, but not super accurate. And again, this is only for gaseous molecules, only the average values, and that's where a lot of that error comes in. So here's another example looking at this. So if we want to find the delta H of this reaction, I have to look up each piece. So we have 4 moles of the NH broken, 1 mole of the NN broken, bonds formed. I'm not sure where that D is there. And again, I just look up the values to the 4 of the NH, 1 mole of NN, 1 mole of the N, I think that's supposed to be triple bond, 1 mole of 2 moles of HH right there, reactants minus products, I get my answer. That reaction is likely exothermic. Bond enthalpy and bond length. So again, just like we can find average bond enthalpy, we can also estimate an average bond length. General rule, more bonds, like moving to double or triple bonds, more bonds there are, the stronger they are, the shorter they are. As atoms get larger, bond length decreases in general. And that, willing participants, is our chapter. Hey, look, picture.